Alrighty then. We're starting a new chapter today. New chapter section, I guess. Not a new chapter. 2.3, other properties of functions. That implies that we've already studied a property of a function. Have we? What property of functions did we just get off of studying? Limits, which helped us deal with. It rhymes with continuity. 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 There we go. So continuity is a very, very important property of a function. In this section, we're going to learn about all the other properties of functions. And then in chapter 3, we're going to start looking at all the properties of functions that we're learning in chapter 2, and we're going to be applying them to separate families, like polynomial families, rational functions, exponential functions, log functions, and then we'll end the year with trigonometric functions, okay? So right now we're just kind of looking at generic properties of functions in general. Okay, so let's start off here by saying if the graph of a function is doing anything on an open interval. Now, open interval, I have to kind of tell you what I mean by that. We mean open X interval. Open X interval. We are going to read a graph like we read a book, not cover to cover, but from left to right in increasing order of X values. That's how you read a graph. So sometimes we'll write the interval like this. The open interval kind of looks like an ordered pair. But in the context of what we're doing, it's not an ordered pair, it's going to be an interval. We say this is the interval from A to B, not including A or B, and of course A has to be less than B for this to work. Sometimes we'll put an X epsilon in front of there just to kind of reiterate that it is in fact an interval of X that we're looking for. All right? So if you have a graph on any open interval doing something, if it exists, it's doing one of three things. It's either going uphill, going downhill, or it's boring, it's staying the same, from left to right. If you read a graph from right to left, you're thinking the first one is decreasing, and it's not. When we read from left to right, this is going uphill, so it's increasing. This is going downhill, so it's decreasing. And this is staying the same, so it's constant. Now, there are several ways a function can increase. It can increase at a constant rate like that, or it can increase at an increasing rate, or it can increase at a decreasing rate. So it can actually have curvature to it. Same goes with the decreasing. It can curve at an increasing or decreasing rate or a constant rate. Unfortunately, there's only one way to stay constant, and it's just to be boring. Okay? So here we go. Here's a little graph. When you read the graph from left to right, if your y values are going up from left to right, that is, a y value is bigger than a y value to its left, you know that the graph is increasing on that interval. If the graph is going downhill, that is, a y value to the right is smaller than a y value to the left, then it's decreasing. What we're going to do is we're going to look at graphs right now and determine the intervals where the function is increasing or decreasing or constant. And when I say find the intervals, I mean what intervals? X intervals. We're going to look from left to right and find the values of X where the Y values are getting bigger or the Y values are getting smaller or the Y values are staying the same. So to help us do that, we're going to look in on Grandpa George. Grandpa George has found the fountain of youth. The last 5 years I've done this example, Grandpa George has been 80 the whole time. He's never gotten older. It's amazing. Okay?
This says he was like 60 pounds.
He was. Grandpa George used to get older, but since I wrote him into example 1, Grandpa George doesn't get older anymore. But we're going to look at the graph. Grandpa George, like most grandpas, he's sitting in a rocking chair and he's reminiscing. And he's reminiscing about how over the years his weight has fluctuated dramatically, okay? And he has a thought bubble going on. If you were to look at the thought bubble that Grandpa George has, you would see this inside of his head. That's what he envisions inside of his head. Pretty impressive, right, Grandpa George? Maybe he was a math teacher in a former life. Who knows? Now, as good as Grandpa George is at recalling such elaborate graphs, he has kind of forgotten what it means to be increasing and decreasing and constant. It's amazing what people forget. Glenn Campbell, the country music legend, just passed away. He had Alzheimer's disease. And there was a documentary on him. And even with Alzheimer's, advanced stages of Alzheimer's, he couldn't remember the words to his songs. But he was such a phenomenal guitar player, he could pick up guitar and just play as if he was playing back in the day. He never forgot a guitar lick, but he couldn't remember the lyrics. It was kind of interesting. So the things that we remember when we're older or we forget, it's kind of interesting the way the brain works. So Grandpa George can remember this, but he forgot about increasing, decreasing. So guess what? We're going to help him. We're going to help him. We're going to look at this graph, and we're going to list the open intervals of X, where X now represents Grandpa George's age in years, where the Y values, which represent his weight in pounds, are increasing, decreasing, and staying the same. So, if you look at Grandpa George, when he was born, he weighed how much? 0. Ooh. He was a supreme preemie, we say. Didn't weigh anything. So, let's start off by listing the intervals where his weight was increasing. So, here's how you're going to do it. You can put INC for increasing, and then a colon, and now we're going to list the intervals. The open X intervals, okay? So, he was increasing from 0 with a parenthesis. We're going to do open intervals. Up to what age? Yeah, it looks like 25. Now, that's pretty impressive. He started out weighing absolutely nothing, and then he gained weight at an increasing rate for the first 25 years of his life. Okay? His weight increased at an increasing weight until he got up to 150, which was his fighting weight, I guess. Was there any other time in Grandpa George's life where he was gaining weight or the graph was increasing also? Yeah.
At 35.
Something happened at age 35 because he ballooned to 200 over a 5-year period. So when we link two disjoint intervals together, we use the union symbol. So now we would say from 35 to 40. Now, anytime you have units in your problem, you have an application, you need to make sure you're putting units on your final answer. Since that was the last interval we're listing, at the back end here, we're going to put YRS, which is short for years, right? So those are the units. Okay, now let's come in and see if Grandpa George lost weight at any time in his life. Where is this graph decreasing? Well, there was that little span from age 40 to 50, right? That decade where Grandpa George went on a 10-year diet, pretty successful diet. He almost got back down to his fighting weight of 150, but not quite. So that's the only interval, so we're just listed as 40, 50, and then years at the end. So was there any time in Grandpa George's life where he actually maintained a consistent weight? Yeah, it looks like 2 periods, from age 25 to 35. So we'll say that his weight was constant from 25 to 35. The union, and he's had a really good 30-year run up to now, right? So from 50 to 80, from age 50 to today, 80 years, Grandpa George has maintained his grandpa weight. Pretty impressive. That's pretty awesome. Yeah, guys, when you hit 25, your metabolism plummets, and then when you hit 40, it plummets even more. So that might explain some of the reasons why his weight fluctuated. So we're done. We're done with the math. Now, what is interesting about this problem is perhaps we can create a story around Grandpa George and why he was gaining weight and losing weight in this manner. So, all right, he was born 0 pounds. Okay? Didn't really exist. He was a supreme preemie, as we say. But he made up for it, right? Over the next 25 years, he slowly but steadily increased his weight up to 150. And yes, as Raina already pointed out, when he was 10 years old, he weighed what? Like 30 pounds, right? Yeah. Did people make fun of him? I don't know. When he was 20 years old, right? Kind of in the prime of his youth, he weighed $1, right? He weighed 100 pounds, probably soaking wet. And then he got to 25, where he maxed out at 150, right? And that's where he spent 10 years at 150 at his fighting weight, man. He was probably exercising a lot during that time, making lots of money. But then something happened at age 35 that caused him to balloon, for George, ballooning up to 200 pounds. What could have happened at age 35 that forced him?
He got wife and kids, and he got stressed, so he ate a lot.
He got wife and kids and got stressed, so he ate a lot. He turned to food for comfort. His wife must have been a good cook, too. Would you say that if he got married?
Yeah.
Or was he eating fast food the whole time because his wife wasn't a good cook?
Both.
He was eating twice every meal. His wife's food, and then he'd make a run to the Mickey D's and get himself a couple of Big Macs. Okay. And he did that for 10 years. He did that for 5 years. And he ballooned at 200 pounds at age 40. But then at age 40, something happened that caused him to go on what looks like a 10-year diet to get back down to his other weight. What happened at age 40? He saw a mirror. He finally looked into a mirror. He had a midlife crisis. Remember I told you your metabolism plummets at 40, but George kind of defied the plummeting metabolism. You know what probably happened, because it happened to me. He went to see his doctor, and the doctor says, hey, we've been looking at your numbers. We found Big Macs in your blood, right? You've got high cholesterol, and you're pre-diabetic there, George. You need to make some changes. So that could have been the reason. Someone suggested last period that he got a divorce and started putting himself, out there on the market again, so he needed to start looking better. I don't know.
That makes sense.
But once he got to 50, for the last 30 years, he's maintained about $160, 160 pounds. So I don't know. Maybe he got over his depression. Maybe he found another wife that was I don't know, a good cook and gave him good portions, and then took away his car so he couldn't drive to McDonald's.
Was a bad cook, and he didn't eat anything. So.
Oh, maybe so. Well, he was eating something because he wasn't losing weight, but he was maintaining it. I don't know. And that's why he's lived to be 80, perhaps. I don't know. So that could have been the story of Grandpa George. All right, so the point of that problem wasn't really to come up with a scenario around Grandpa George, but to use the graph to come up with these intervals. And it was pretty easy, right? I mean, it wasn't difficult. If you have the graph, you have your eyeballs that you can use to look at the graph to determine where something's going up or down or not going up or down at all, right? Pretty easy if you have the graph. So here we go to example 2. It says for each function, without a calculator, okay, no calculator on this one, list the open intervals on which the function is either increasing, decreasing, or constant. Do it without a calculator. Okay, I got it the first time. Gosh, a sketch might help. It was so easy with the sketch on Grandpa George example that the way I want you all to do these, or the way that we're going to do these, is to sketch a graph. So this is going to require a little bit of knowledge of some parent functions and some transformations. So take a look at f of x equals 3x cubed. What's the parent function? X cubed, right? And when you think of the x cubed graph, you should be thinking of John Travolta on the cover of Saturday Night Fever, right? Looks something like that. Looks like that. What does the 3 do to it? Stretches it how? Vertically by a factor of 3. So that's like John Travolta dancing, right? His hands go up and down. That makes the graph a little bit steeper, and it looks like that. So the green graph is now the function we're interested in. You should know that the cubic function right there at x equals 0, at that point, has a 0 slope. It's a stationary point, we call it. A stationary point. So you can kind of think as some of these people are climbing a mountain, right? And it's a trek upward. And right there at 0, it flattens out horizontally for a single point. And that might be enough to set up a tent, and tie it into the mountain on the other side to sleep for the night before they start the arduous trek again in the morning up the next branch. But that is not constant on any given interval, okay? It's only constant or flat at a single point. And since we're looking for the intervals where it might be increasing, decreasing, or constant, we can actually say that it's not constant on any given interval. So this graph, if it's doing anything, it's doing what from left to right? Increasing or decreasing? It's increasing. You could say it's even increasing through that stationary point. If it were an interval, if it spanned between any 2 points, we'd have to list it as a constant interval. But it's only a single point. So we could say that this function is increasing from where to where? What would the interval be if it's everywhere?
Infinity.
Negative infinity on the left to positive infinity on the right. And we're always going to do open intervals. Infinity and negative infinity always get parentheses anyway. So a function that is doing one thing and one thing only, we say is monotonic, or strictly is another word we can use, increasing. And this function is monotonic increasing over its entire domain. It's monotonic increasing Monotonic meaning what? One, right? Like monosera means one Sarah is allowed on the team at a time. Monotonic means one tone, right? One tone. It's doing one thing and one thing only. Or strictly increasing, meaning it's only doing that and nothing else. This one's doing it over its entire domain, and of course the domain is all real numbers. All right, letter B. Take 1 minute on your own, or at home if you're watching the video. Take 1 minute and graph that parent function by using transformations. And then if you get done with the graph before we come back together, answer the question. Where is it increasing? Where is it decreasing? Where is it constant? We'll use the calculators on the next example, but not on this one. The -4 is on the inside of the function, so it's going to affect the graph horizontally, not vertically. All right, I see a lot of graphs manifesting. That's good. Most of y'all have the parent function down. The parent function is x squared, which bounces at the origin and opens up. What does the negative in front of any function do, including this one? It's an x-axis reflection, right? Your y values are opposite of what they used to be. Like a +5 is now a -5. That's a reflection across the x-axis. That's going to make the parabola open downward. What would the 5 do on its own? Yeah, kind of like the 3 did in the previous problem. This one's going to stretch it vertically by a factor of 5. That's just going to make it a little bit steeper, kind of like that. The -4 is hugely important. That's going to shift it where? Left, right, up, or down 4? Right 4 units. Okay, so to draw it, here's 4, and now I'm just going to draw it about 5 times steeper than I normally would. And if you look at that, you can be like, man, that was good. That is about 5 times steeper. I would say thank you. And that would be the same criteria I would use when I look at your graph. Okay, so now that we have the graph, it looks like it comes in from the left doing what? Increasing or decreasing? Increasing. So where would it start increasing? It would be increasing from -infinity all the way up to 0, question mark? 4. I see this kind of stuff a lot of the times, -infinity to 0. What am I, or what would this person be doing if they listed -infinity to 0? They're listing the y values, right? We don't list the y values. We're looking to see where are the y values going up for what values of x. We're not listing the y value interval. We're saying from x equals -infinity up to x equals 4, your y values are increasing from, if you want to say, -infinity up to 0, that's fine. And then on the right-hand side, there's another stationary point up here, by the way. That's a stationary point because it is constant right there at the top, which it doesn't matter. That's why we use open intervals. This one is decreasing to the right of 4, so from 4 to infinity. So this is all local behavior that we're looking at today. And look how exciting that one is, right? Very exciting. It goes up, and then it goes down. Woo, almost like a ride at the fair, right? It goes up, and then it goes down. Let's ride it again. It goes up, and it goes down. You see how exciting local behavior can be compared to the boring end behavior of a graph? Yeah, yay. Okay, sweet. Take 45 seconds, not a minute, and sketch this one by transformations. And then answer the question, where is it going up, where is it going down, where is it staying constant? All right, the parent function is 1 over x. The reciprocal function, 1 over x, has a vertical asymptote at x equals 0, horizontal at y equals 0. The reciprocal of a positive number is positive. The reciprocal of a negative number is negative. The reciprocal of a small number is a big number. And the reciprocal of a big number is a small number. So that's why it looks like that. The 5 does what to that graph? Makes it 5 times steeper vertically. Yeah, so we don't really even show that. But the plus 3 is important. It moves that entire graph which way 3 units? Left. Now, if you weren't sure if it moved to the left or right, you could actually say, hey, negative 3 is not in the domain of this function. And when you plug it in, you get 5 over 0. That means there's a vertical asymptote at negative 3. But that's the same thing you would do if you just shifted the graph over. So there's a vertical asymptote there and a horizontal asymptote. If your graph ever has asymptotes, you want to draw them first because they become like guidelines for your graph. So now that I have them drawn in there, now the graph looks something like that, and the graph looks something like that. And now I can answer the question, where is this graph increasing or decreasing? Well, let's come in from negative infinity. As we come in from negative infinity, this graph is doing what? Going up or going down? It's going down, right? So I'll start off with the decreasing interval. It's decreasing from negative infinity up to what? Negative 3, the x value. Cool. You found it? Good. All right, now just on the other side of negative 3, as we move out to the right, what is it doing now? Is it going up or down? It's still going down. That's weird. It kind of like went through a wormhole. To the left of negative 3, went down to negative infinity, and then whoop, popped up on the other side at positive infinity. Infinity. So from negative 3 to positive infinity. Would you say this one is monotonic over its entire domain? Would that be fair to say? Yeah, this one is monotonic, decreasing over its domain. And of course, its domain is what we just listed above then. Negative infinity to negative 3, union negative 3 to infinity. Monotonic or strictly decreasing. DEC is how I write decreasing. Okay, so it's never increasing and it's never constant. So when you have the graph, things can be easy. All right? So what we're going to talk about now is another vocabulary word. We're going to look at extreme values here. This point right there, 4, 0, is the vertex of that parabola. And although it is a stationary point because it's increasing on the left and decreasing on the right, it's a little bit more exciting than the stationary point at x cubed. We call that y value right there a local maximum. Okay, it's a local maximum value. It's an extreme value. Okay, so let's define it. If you talk about local maximums or local minimums, the generic term for a max or a min is called an extremum. And I meant to highlight it. An extremum. That is either a local max or a min. The plural is called extrema. Extrema is plural. And it can mean a local maximum or a local minimum. So let's talk about what makes it a local max or a local min. If you look at this graph over here, it looks like a parabola. It might be a parabola, but there's a vertex then at h comma k. We call this a local minimum because in this locally small, relatively small interval of x, it is the lowest y value. Instead of local, sometimes we use the word relative. It's exactly the same thing. A relative minimum and a local minimum are the same thing. I like the word local, okay? The minimum value itself, though, is the y value. That's important. The minimum value, the extreme value. What makes it an extreme value? The fact that it goes kayaking on the weekend over waterfalls drinking Mountain Dew. Does that make it extreme? That would be one kind of extreme. What makes this an extreme value is because it's locally the lowest point. Same thing as a local max would be extreme because it's locally the highest point. So the minimum itself is the y value. It occurs or happens at an x value. So here's what we would say. We say that this graph has a local minimum of y equals k. It's the k value, that's the minimum, and it occurs at x equals h. The minimum value is the y value. Similarly here, we have a local maximum, also called a relative maximum, and there's a misprint right here. It says local min. Scratch that out. Call that a max. You can abbreviate minimums and maximums as min and max. That one is a local maximum, again, of y equals k at x equals h. All right, so you can actually have several local maximums or several local minimums on any given function. Just like you have local mayors in each municipality, right? There's a local mayor here, there's a local mayor in Seguin, there's a local mayor in San Marcos. In their relatively small region, they are the local max or min of their region. But you also have what's called absolute max or global max and mins. And I'll tell you how to find those too. So I tend to use the word local max and min and then global max and min. They kind of go nicely. Mr. Wenzel and Mr. Brake would be proud. They're geographic terms, right? Locally versus globally. We shouldn't be ethnocentric. We should always think globally. So the global min, there could only be one if there's any at all. Okay? We have many local mayors, but there's only one supreme mayor, right? And right now his name is Trump. So you can only have one at most global max or global min, but you can have several local max or mins. So here's what we're going to do. With the help of a calculator now, because we know how easy it is to find local max and mins from the graph, we're going to use the calculator to sketch these functions. So now if you have your calculator, go ahead and get it out. And we're going to type into y1 that function right there. We want to see what the graph looks like. So if you don't have a calculator, you could just look on up here. I'm going to use the math print mode. If you have one of my 84s, you are default in what's called math print, which is kind of pretty. It writes using math symbols. Some of y'all have an 83, and I'll show you how to do that as well. You type in x to the fourth. With math print, when you hit the caret, it puts you up in exponent land. So all you have to do is hit a 4 and then click to the right to get back on the ground floor. If you're in classic print, when you hit the caret, you'll actually see the caret. You just type in a 4 and go on to the next term. Minus, oh, I'm doing it in the wrong spot though. Here we go. X to the fourth. Do it in y equals minus 7x squared. And there's a squared button that automatically squares it and puts you back down on the ground floor. And then plus 6x. So instead of just hitting graph, the best place to start any graph, if you're not sure what it looks like, is in your standard viewing window. So don't hit graph, rather come up here and hit the zoom button. And then number 6 is standard. That puts you in a negative 10 by 10 window. So zoom 6 is always where I start graphing. Zoom 6. All right? So notice this graph looks like it's coming in on the left from positive infinity. It looks like it's going to turn around down here somewhere off my screen. Comes up, turns around again. So anytime you have a vertical about face, you're going to have a local max or min, a local extrema. We need to adjust our window, though, to see the bottom point here. So go to your window now, right next to y equals. Scroll down to y min. We need to make it a little bit lower so we can see. So let's try negative 20. Once you start changing the max and mins, I like to go to the y scale and just turn it off by putting a 0. You don't really need the tick marks. And sometimes if you stretch your axis out too far and you have the calculator put a mark every unit, you get what's called fat axis. And like Grandpa George, you want to avoid fat axis at all possibility. So I just turn it off. I just put it at 0. So now hit graph and we'll see if we actually, oh, mine graphs pretty quickly. I don't see the bottom yet, so I need to go back to the window and adjust it even more. My y min, negative 30. Let's try that. And hit graph. There we go. Now we can see everything. So the graph comes in. This vertical about face is going to be a local what? Min or max? That's a local min. In this little vicinity down here, that's the lowest value. That's a local min. Then we come up here, and this is a local what? Max. In this small vicinity, he's the highest point. Then we have another local min right down here, because in that vicinity, that's the lowest value. And then it increases without bound. So it looks like we have 2 local mins and 1 local max. Bless you. Now let's talk about absolute min and absolute max, or global min and global max. Is there a global minimum? Is there one y value that is lower than all the other y values on the entire graph? Yes. This one down here. This is a local min, and it turns out that it's the global min. Do we have a global max? No, because this graph goes up to infinity on both sides, it's unbounded above, so there is no global max. All right? So we have a local min that is also the global min. We have a local max and another local min. So here's how we're going to find them. From the graphing screen, hit second trace. Second trace goes to your calculate menu, and let's find the minimums first. Guess which one we're going to choose for minimum? Minimum. Right. Number 3. So it's going to ask you for 3 things: left bound, right bound, and guess. You can scroll to the left of your first one. So once you see the cursor blinking to the left of where the first one is, hit enter, and you've anchored that point now as the left endpoint. Now it asks you for the right bound. So click to the right until you're to the right of the low point. And just make sure you're to the right, get a good visual, hit enter. And now for your guess, you don't have to guess. You could just use the right endpoint as your guess. It's kind of fun to shout out a guess while you hit enter. 7! I was way off. It was negative 24. Okay? For your guess, just hit enter for the right endpoint. It'll scan that interval, and it'll look for the lowest y value, and it puts you right on it. So now it tells you the minimum is this. But which one of those is actually the minimum? The x or the y value? The y value. And if you read in the parent letter, you know that if a value does not terminate prior to, or doesn't terminate at all, how many decimals are we responsible for reporting? Rhymes with tree. 3. Very good. 3. You have to report 3 decimals. You can round or truncate. Rounding means rounding. Truncating means don't round. And I'm a big fan of non-rounding or truncating. So I'm going to put on my paper now, as you write it as well, local min of y equals negative 24.057 at x equals negative 2.056. Okay, so here's what I wrote. Local minimum of at. Whenever you say the word of, a y value is about to follow. Whenever you say the word at, an x value is about to follow. And I truncated. I didn't bother rounding. Save that mental energy for other stuff. All right, now let's go ahead and find the other local min. So we do it again. Go back to the calculator. Second trace, number 3 again. Now, if you don't want to scroll, because sometimes that could be a bother, notice I'm counting by ones on my x-axis. It looks like my other local min falls between x equals 1 and 2. So for your left bound, you can actually just type in the number 1 and hit enter. And then type in the 2 and hit enter. It's not as fun as scrolling, but it's a little bit faster maybe. And then hit enter for your guess. And now you write it down again. We have another local min of y equals negative 1.766 at x equals 1.600. If you truncate, it's 600. If you round, it's 601. Do you need to put both of those zeros in your answer for 3 decimals? Or can you just put 1.6? You actually need the zeros. Here's why. If it were like 1.6 terminate, then you can add zeros forevermore after that, and you're not going to get any more accurate. But these aren't just trailing zeros. These are zeros that represent part of the accuracy, because now we pick up with other numbers. So don't leave off those zeros. You need them if you truncate, or put 1.601 if you round. But you need those zeros. If you leave them off, you lose points. All right? If you're ever off in the 3rd decimal place, you're going to lose points. Now let's find the local max. We do it again, second trace. But this time, for maximum, we're going to choose, guess what? Maximum, yeah. And I'll go back to the scrolling. It was fun. So from the left, there it is. Hit enter. I'm going up, and then it's coming back down. Hit enter. And then for your guess, hit enter again. And it tells you right there. It'll blink where it's at. So now we have a local max of y equals 1.323 at x equals 0.455. And these, you have to have the word local in front of them or the word relative. Relative max, relative min, same thing. If you just said min, and max, you'd be wrong. Okay? And I'll tell you why here in just a second. So that takes care of the local extrema. Let's go back and look then for the absolute extrema. There can only be at most one of each type of global or absolute extrema. And we know we have a global min. And we've already found it. So let's go ahead and say we have a global min of, it was the top one, y equals negative 24.057 at x equals negative 2.056. Now, instead of using the word global, you could say absolute. Usually, if you say relative max, relative min, then you refer to absolute max, absolute min. They kind of pair up nicely. But if you use local max, local min, it pairs up nicely with global max or global min. But here's the deal. If you do not say what type of max or min it is, whether it's local or global, if you just said minimum of y, guess what everyone in the world is trained to infer? Global, right. If you don't say what type of max and min it is, then everyone's going to assume you're talking about global, which is why it's important if you are talking about the local max and mins, of which there could be many, you have to say local or relative. Otherwise, you're going to be wrong because you're talking about absolute or global. So to avoid the confusion, I just like writing the qualifiers in front of them. Local and global are what I typically use. Okay? Yeah.
Would you take off if we did?
No. If you did not put anything and you knew that an absolute min and the global min were the same as just the min, you could just say minimum of y equals. That's fine. I'm fine with that. But if you don't put the word local or relative on those types, you're going to lose points. Okay? So yeah, with that said, since you asked, Dane, I'm just going to leave it. I'm just going to leave it like that. I'm just going to say minimum of y equals. But know that it means global / absolute. All right. Let's do the next one together. U of x, right? U of x, that's an interesting one. Let's go to the calculator for that. Go to y equals flush to get a clean bowl. There it is. Now you got 3 parentheses, x minus 4. Close. I'm going to do this one, by the way. I'm going to go to my mode, and I'm going to switch to classic. If you have math print, keep going. If you have the classic, which means if you have an 83, if you have a black calculator, it's going to be 3 parentheses x minus 4. When you hit the caret now, you don't go in exponent land. You must put parentheses around your exponent, 2 divided by 3. Otherwise, it's only going to exponentiate to the second power. So there's a little bit more parenthesis work if you have an old school 83, but it still works. And then minus 2. If you have math print, make sure you click to the right after you type in 2/3 so that you're back on the ground floor. So I'm going to hit zoom 6 now. And this kind of looks like a seagull, right? On your seascapes you drew in 2nd grade. No seascape was complete without a couple of these seabirds, right? It looks like it only has one local min, which happens to also be the global min, right? No maxes at all. So to find it, we hit second trace. Guess which one? Number 3. Am I to the left of it? Yeah, I'll just hit enter. And then 1, 2, 3, 4. I'm going to go to 5 for my right bound. I'll just type in 5. And there it is. So you don't have to make the interval super small. Just make it an interval and then hit enter for your right endpoint. So there you go. Let's write it down. We have a local min and a global min. I'm just going to put them all in the same. Of y equals what? Negative 1.999999802 is not the right answer. Your calculator is a liar and a stupid computer box. You're the brains of the operation and you're the boss in the relation, okay? This is your calculator's way of saying -2. If you ever see at least 3 9s followed by another big number like an 8 or another 9, that's your calculator's way of saying, hey, you better go to the next nearest integer. That's your calculator's way of saying -2. And it occurs at x equals 3.999999995 is your calculator's way of saying 4. All right? So, again, if you see a string of 9s, 3 9s at least with another number behind it, that's either an 8 or a 9, you're rounding to the next number. So it's -2 and 4. Look at your equation. Do you see a 4 and a -2 in there anywhere in your equation? Yeah, it almost looks like that graph was picked up, moved right 4 units, and taken down 2 units so that the vertex is now at 4, -2. So there's evidence in the question, too, that it has to be that number. So that's what you're going to write down. There's a local min and a global min of y equals -2 at x equals 4. And we're done.